this lecture, I am going to talk about a rule, or what is also called as the Wies zone law. Now, first let me take a cubic unit cell first. So, suppose I have a HKL plane, and a direction UVW which is lying in the plane. Then, as we had seen in the previous lecture, clearly if the direction UVW has to lie in the plane, then the dot product of this direction UVW with the normal to the plane HKL should be 0. And we have seen from the previous lecture that normal to HKL is the direction with the same indices HKL, which implies that the vector UVW dotted with HKL should be 0. And if I take the dot product on the left hand side, then I just have to multiply the corresponding indices in the two vectors. So, HU plus KB plus LW would be 0. Now, this I have specifically shown it for a cubic unit cell, but this is a very general expression valid for other unit cells as well. And now it will be my endeavor to derive the expression in a much more general way, because here we have just derived it for a very specific case. So, let us see how we can derive this. Again, let us take a arbitrary HKL plane for an arbitrary So, I have an HKL plane here, but this time this HKL plane is not in a cubic unit cell, it can be in any unit cell. But again, the intercepts of this plane HKL would be A by H as before with the A axis, B by K with the Y axis, and C upon L with the Z axis. Let us consider two vectors lying in the plane ABC. So, consider the vector, let us say AB, and consider the vector AC here, and let us write the expression for these vectors. So, vector AB. So, vector AB can be decomposed into two vectors, and the two vectors are going to be AO for plus OB. So, you start from point A, go to the origin through the vector AO, and then travel along the vector OB. So, I go A to O, O to B, and I reach the point where this vector AB joins. And it's as you can see in the previous lectures, it is straightforward to write this vector in terms of A and B vectors of the unit cell. So, this would be B by K minus A by H. Now, let us write an expression for vector AC as well. Vector AC, so travel along the vector AO and then move along the vector OC. So, AO is a vector OA, so that is minus A by H, vector OC is simply C by L, and hence I can write this as C by L minus A by H. Now, consider another direction which lies in the same plane, and let that direction be something like this, whose Miller indices are U, V, W. And let me call this vector in the following way. Let us call this vector as R, and this vector R I can write as U times A bar plus V times B bar plus W times C bar. So, if I now take these three vectors AB, AC and the vector R, if I take what is called as the triple scalar product, then that can be written as R, vector R dot, and take the cross product between AB and AC. So, this is called as a triple scalar product, R dot AB cross AC. So, AB cross AC in the parenthesis would give me a vector which is going to be perpendicular to the plane ABC, and hence it will also be perpendicular to the vector R, which is a direction lying in the plane, and therefore, the dot product between this resulting vector which is normal to the plane HKL with vector R should be 0, which simply means that the three vectors one should be able to express in some linear combination. So, in fact, one can write, because of this, though I am not going to specifically prove this, I can write some scalar quantity S times the vector AB plus another scalar quantity, let us say T, times the vector AC, and a third scalar quantity, let me call this as the quantity, let us say Z, times the vector R. This sum should be equal to 0. So, this can be written in another form as the vector R. I can rearrange these terms and then divide everything by Z. So, I end up as the vector R to be equal to P, some quantity P times the vector AB plus a quantity Q times the vector AC. So, essentially what I have done is I have expressed the vector R as a linear combination of the vectors AB and AC. Now, let us move a bit further. Let us substitute for the vectors AB and AC this expression, which is in terms of the unit cell vectors A, B and C. So, if I do this, I am going to get vector R, which also let me write down the expanded version of R as well, which would be U A bar plus V B bar plus W C bar, and this is on the left hand side I have written. Now, for the right hand side I substitute for vector A B. So, if I substitute for vector A B, I will get minus P times B by K, vector B by K, minus A by H, and for the vector A C, I am going to get Q times C by L minus A by H. Let us rearrange these terms, and this will become minus P plus Q divided by H, and this whole thing multiplied by the vector A plus I can have another term which would be P upon K times the vector B, and a third term Q upon L times the vector C. Now, let us look at this. If I look at, for the vector R, I have U A bar plus V B bar plus W C bar, which is equal to minus P plus Q upon H A bar, P by K B bar, Q by L C bar, which implies that the corresponding terms. So, U has, for vector R to be equal to this quantity, this must be U, this would be V, and this quantity would be W. So, I can write for UVW, I can write U equals minus P plus Q upon H, V equals P by K, W equals Q by L. Now, let's look at this expression here, and let us see what we get. HU plus KV plus LW, and in this expression I substitute for UVW, and I am going to get minus P minus Q plus P plus Q, and you can clearly see that everything gets cancelled and this becomes 0. Now, here we had made no assumptions regarding what unit cell it is. So, therefore, finally, I have a general, or the expression HU plus KV plus LW equals 0 for any unit cell. So, ABC can be anything, alpha, beta, gamma, the angles between the ABC vectors can be anything, but this expression will hold. So, this is what is called as the Wies zone law. Now, let us just take one application of this law. We can use this to find, so let us find a common direction between two planes. That is basically essentially what we are trying to find is the line of intersection of two planes. And as an example, let us consider 1, 1, 1 and 1 1 bar 2 planes. So, this is just an example here. Let u v w be the common direction, which basically means the direction u v w should be lying in both the planes. So, let us apply this V zone law. So, first we will take the first plane 1 1 1. So, for 1 1 1 plane I have H u plus K v plus L w is equal to 0. I multiply the corresponding indices and I get u plus v plus w equals 0. Now, I apply the same law now to the plane 1 1 bar 2, and this would be, I will get another expression u plus v minus 2 w equals 0. So, let us say this is equation 1, this is equation 2. So, let us first subtract equation 2 from equation 1. Subtract 2 from 1 and I will get clearly 3 w equals 0. So, implies my third index for that common direction is 0. Now, I can do multiply 1 by 2 by a factor of 2 and add to equation 2. Then if I do the addition, first multiply, the first equation will become 2u plus 2v plus 2w equals 0 and then add it. So, w term will disappear and I am going to get 3u plus 3v equals 0. This implies that u equals minus v, and therefore, now I have the indices u, v, w in the form u bar u 0. Now, I can divide everything by u and this would give me the Miller indices for the common direction is 1 bar 1 0. Of course, I did not need to do all this thing by multiplying by 2 and then adding equation 2, because since we have already shown that w is equal to 0, directly from either of the equations 1 and 2 I will get u equals minus v. So, this direction 1 bar 1 0. Let us also look at how we can do it geometrically. So, if I do this geometrically for the plane, so let me just write down these planes 1 1 1 and 1 1 2 bar, and my common direction is u v w. So, if I, so this is the common direction. So, for this common direction, so let us draw this in a unit cell. Again, I am going to draw it in an arbitrary unit cell. So, first let us draw these planes. So, let me draw first the 1 1 1 plane. So, again I must always say where are my axes. So, A, B and C axes. I can, so the 1 1 1 plane would be like this. So, its intersections 1 along x and 1 along y and 1 along z in terms of fractional coordinates. Now, let us look at the plane 1 1 bar 2. Instead of drawing 1 1 bar 2, let me take just negate all the indices, bar 1, bar 1, 2. Now, what would be that? So, going back to our definition for Miller indices, I will take reciprocals. So, I will get minus 1 along x, minus 1 along y and half along z. So, what I could do is I could change my origin. So, this becomes my origin, and so these are my axes A, B and C. So, clearly minus 1 intersection along A would be the intersection here, minus 1 along B axis, or rather B axis, the intersection will be here, minus 1 along A axis, the intersection would be here, and hence my plane 1 1 bar 1 bar 1 bar 1 bar 1 2 would be this, while this is 1 1 1. In this figure itself, it is very clear that the common direction is along the face diagonal in this way, and clearly the common direction its Miller indices, and you can find out. You could shift the origin, for example, out here. So, if I make this as the origin now, then it is 1 along A, minus 1 along B and 0 along C, and hence the common direction then would be 1 1. It is 1 bar 1 0, and it is the same result that we had got out here. So, I deliberately changed my indices, I negated the indices, still remains the same plane, but suppose I did not change the indices. Then what I could do is I could shift my origin out here. So, this becomes my origin, and I use these indices 1 1 bar 2. So, that would be clear then, this plane would be intersecting 1 along x axis, 1 along y axis and minus half along the z axis, and therefore, minus half here. I will get the plane. So, this one but remember, the two planes are really not different, they are just drawing belongs to the set of the same parallel planes. But here, if I look at what is the direction or what is the intersection of the two planes 1 1 bar 2 and 1 1 1, well, look at it here, there is a point on the left face and another point on the rear face, and if I draw a vector, let me draw this in different color. This is my vector, and you will see after carefully considering it that this vector that is drawn, let us say if this vector is r, then this vector r bar is clearly parallel to 1 bar 1 0, and hence the direction Miller indices of this would also be the same. But the way I have drawn it, this vector, if I were to write the Miller indices, it would be bar 1 1 0. If I represent this vector like this, then the indices is going to be 1 bar 1 0.